Hi, and welcome back to Book Club. And if it's your first time joining on one of these book clubs, what I'm doing here is there's some great engineering textbooks, like this one we're going to do now in this book club, Rocket Propulsion Elements by Sutton and Biblarz. This is a great, kind of all things rockets. And the point of book club is you don't have to go register for a graduate course. You don't have to go do this. These books are awesome. And what I'm trying to do is in little short 15 to 20 minute segments covering a chapter or maybe sometimes a couple of chapters is just give you the high level thing so that all you have to do, maybe just listen to me and then dig into the book and you're going to now know the subject in and out, right? This is I've always been an avid reader and, ever since getting my PhD, I'm able to just keep reading and keep ingesting and keep learning. So book club is a great way to do this, to sort of arm yourselves, so go rent it from a library, go buy it. This is a great book. And so on this first one, we're going to get into really actually the first couple of chapters. Reason being, at Venus Aerospace, my company, actually I've done a little bit of kind of a Rocket 101. So I'll sort of put a link up here on just some basic Rocket 101 stuff, how do rockets work, fuel and oxidizer and things like that. And so that's kind of the chapter one that's sort of inside this Rocket Propulsion Elements book. It's just that one. So you can go look at that one, or really, I'll kind of start here basically in chapter 2, where it's really, I'm going to draw a very simple rocket engine, okay? And what you're doing on a rocket engine is inserting fuel and oxidizer. And I know this is red, and I know red doesn't always come out so well. Yeah, that's not come out so well. Let's see if my orange is doing better today. Yeah, there's some orange. Okay, and so what you do in a rocket engine is you have a fuel and you have an oxidizer, and you push them in there, they react, and this is basically taking chemical energy, converting it to thermal energy, and then this throat, this really hot stuff is now high pressure and gaseous. The throat speeds things up to about Mach 1, and then the nozzle increases that from Mach 1 to Mach, higher. Now, this is not Mach 1 like we normally think of here on Earth. This is local Mach 1. So Mach actually goes like the square root of gamma RT, so temperature basically, gas constant and ratio specific heat. So this is a very, is Mach 1, it's not our normal sort of here on Earth Mach 1, okay? And from a conservation of momentum point of view, what the actual thrust that you're getting from this is the amount of mass flow rate, so that's usually m dot, times the exit velocity, that's this stuff here. So this whole thing is now screaming out at some v exit, okay? But the pressure doesn't always match. And so you also then have sort of this, they usually say P2 minus P3 times A2, where this area here is A2. A lot of times this is called area throat. And what you're doing is just, P2 is sort of the pressure here associated at the exit plane. Now, if P3 and P2 are matched, then this is actually a perfect nozzle. And we'll go through some of this, right? And then sometimes, as P3 goes to 0, right, that would be in the vacuum of space, then you get a little bit more thrust. Sometimes it's not as efficient. You'll actually get some overexpansion. So this can be a little simple because it's you can get the angle of the velocity doesn't always come straight. But we'll get into some of that. So this is really just kind of the basics. And so then normally the way we look at this, to first order, a lot of times we'll ignore this. And so what we can do is we usually define specific impulse as the amount of thrust you're getting, that's F, divided by m dot. And so again, if we're sort of ignoring the pressure difference, then what you see is this is basically the same as the exit velocity. Okay? But either way, we usually then treat this as ISP is usually written in terms of units of seconds, so we usually also divide by gravity just to sort of do it. So that'll give this in terms of unit of seconds. And maybe that's a weird unit for you to think of. It's actually one of those things where in freedom units, you can think of ISP as force in terms of pounds force divided by the pounds mass per second, and there's a kind of easy way to think of that. Okay? And, what you end up getting is ISPs as sort of you're going, increasing in altitude, your ISP, so your efficiency, right? How much thrust you're getting per fuel may start low and then will increase as you get into altitude, and really is dependent on the size of the nozzle. Okay. Now this curve, say 255 at sea level, up to 290 seconds. Okay? That was the RS-27. That was on many launch vehicles for Delta II. LOX RP. So that would be where I have the oxidizer is LOX, so liquid oxygen, if you will, and then the fuel is RP1. RP1 is just kerosene. Kerosene usually has all sorts of other stuff in it. So jet fuel is also lots of kerosene, but it's there's all sorts of stuff that comes in jet fuel. So RP1 is just basically kerosene with a good filter to get rid of all the other junk. Okay, and so this is kind of the basics of it. But really, to kind of show you some amazing pictures, and we'll get into some of this. Like this is Starship and the Raptor engines, and so this one would be liquid oxygen and methane. And man, what a glorious sight this is! I hope, if you're an engineer, you better not have missed some of those launches, especially the one where they kind of captured the booster back with the chopsticks. So this is pretty awe-inspiring. Okay, this is the Space Shuttle main engine. This is actually the most efficient rocket engine humanity's ever made. We'll come back and talk about it. This one used hydrogen and oxygen. So while the engine was super efficient, if you remember the Space Shuttle, it had to carry that big orange tank full of hydrogen. Hydrogen doesn't pack very well. And so we will talk about it. It's not always just specific impulse. We'll go actually to the systems level equation and show you it's kind of specific impulse as well as the density and structural factors and things like that. So we'll show you. Okay. And then, of course, we even have some crazy ideas that we never flew, but this is NERVA, nuclear reactor, and where you would use a nuclear reactor to, say, heat up hydrogen and spit out the back. Now, we never flew it, but we built it and did some ground tests. And so all of these are considered rocket engines. Okay, and so as we kind of get into it, in Chapter 2, that this really is defining sort of this velocity to the velocity exit, and maybe I'll write it down here so I'm not covering up my face. That velocity 2, as you go into the derivations of Chapter 2 and you're reading through, you'll see, I'll try and write it down verbatim because there's always all of these other terms, 2 gamma over gamma minus 1, RT over M, and then 1 minus P2 over P1, gamma minus 1 over gamma. Okay. So a couple important things in these terms. Now you see up here, basically the Mach number is gamma RT. That's kind of what this is. And so your exit velocity, which is your efficiency, what you are looking for, RT. So R is just the universal gas constant. Gamma is the ratio of specific heats. So a lot of times gamma can be like 1.2 or 1.3 or depending. Air is 1.4. We're not using air here. These are sort of exhaust products usually of carbon dioxide and water. And so, 1.1 to 1.3 is usually what the gammas are going to be. But basically, this whole thing is driven by, you want hot exhaust, you want your temperature up, and then M is your molar mass. So you want your molecular weight down. And so that's kind of back to the NERVA. That's why this is a nuclear reactor, which is, temperatures aren't that hot in a nuclear reactor because you actually have to keep the fuel rods from melting. And so it's sort of, you would say, a medium temperature, but then the molecular mass is hydrogen, which is 2. And so this would actually, these systems tend to have ISPs around 900 seconds, which might sound amazing, but again, at the systems level, you'd have to actually go back and look at the mass of the reactor, which is not small, and then the size of those hydrogen tanks. Whereas a normal rocket engine, the mass of a rocket engine is super tiny. It might be like 2% of the mass of the vehicle. And so it's really pretty impressive. And there'll be some interesting combinations as we get into some later chapters of how much oxidizer and fuel. So in chemistry, if you've taken some chemistry, stoichiometric would be where your fuel and your oxidizer fully react, and all you're left with is water and CO2. A lot of times, rocket engines will run fuel rich, and so what's left is you don't have enough oxidizer to mix with all of your RP1. For example, a lot of LOX RP engines, like we used to do at Virgin Orbit, are fuel rich, and that's because the constituents of the fuel coming out have a lower molecular mass. And so while your temperature might be a little bit lower, your molecular mass of the exhaust products are lower. And then the other one that's kind of trading going back to this engine is they also didn't run stoichiometric here on the space shuttle. So stoichiometric for hydrogen and oxygen would be about 8 times the mass of oxygen to 1 hydrogen. And that's just because, as we'll get into it, how you cool these things, we usually cool it with a fuel. And so there was a limit of how much hydrogen's an okay coolant, but it's not a great coolant. And so while they might want to actually push the O to F ratio right closer to stoichiometric, going more like 7 or 7.5, it was actually the heat flux. They couldn't cool the system well enough. And so most Hydrolox engines run also fuel rich, not from an ISP point of view, but actually from a keeping the engine cool point of view. So these are all the things we'll actually be able to get into this book that are pretty awesome. And I want to finish a little bit here with, we'll get to the rocket equation, a very simple derivation, but just to also highlight for you a few things as we start painting the picture of the rocket engine. While I've drawn something here that's very, very simple, I'll leave this picture here with the space shuttle main engine. You look at all the stuff that's happening up here. There are turbo pumps, there are valves, there are all these things, but there's also something called a gimbal. And so a rocket, sometimes it will have some control surfaces for flight in the atmosphere, but ultimately a rocket, its job is to go up out of the atmosphere and then lean over sideways. And so if here's the Earth, a lot of times people sort of miss this. Space, let's say you're here. This is you standing on the Earth. Okay, while space is up officially, in order to stay in orbit, it's actually sideways. So a rocket launch, it's going to go up to get out of the atmosphere and then lean over and quickly go sideways at about 5 miles per second. Or if you want to think about it in terms of speed of sound, it's like 25 times the speed of sound here on Earth. It's fast, 8 kilometers a second. So space is really sideways. Now also to give you some example of space, if Earth is a peach, the space station that we consider low Earth orbit, and this is not to scale on this diagram, the space station is actually still in the peach fuzz, if you will. Okay? And then we have medium Earth orbits, which is where satellites are, like GPS satellites and things like that. They orbit about every 12 hours. And then we have geosynchronous geo orbit, where actually the orbital period of this is 24 hours. And so as the Earth is rotating, these geosatellites are actually staying over the exact same spot. Now, it takes a lot more energy to get up here, okay? But this is about 6 diameters away from the Earth. And then just for scale, if I even did this right, that would put the moon somewhere over here. So the moon is 30 Earth diameters away. So it just gives you the size and scale of space. We've sent some things to the moon. Yes, we've sent some things to the Mars. But we'll kind of get talking a lot about it. But back to this gimbaling, you're only in the atmosphere for a little bit. And so ultimately you need some sort of system to kind of keep your rocket moving straight. And so that's gimbal, that your rocket engine needs to be able to move usually in some sort of cone, and usually 3 degrees is enough. At Virgin Orbit, we dropped a rocket from a 747. We actually had to gimbal up to 10 degrees just because we had a pretty crazy pull-up maneuver. And so you always have to have that, because you're always going to have some thrust misalignment. Like, I don't care how accurate you think you are in installing this, there could be something going wrong. Like, this thrust could be off by, as much as half a degree, and your rocket is just going to go boink and go right back to the ground. So we'll get into a lot of these systems, but that's one that's mentioned here pretty early in the book, just to sort of set your eyes on what are sort of the details of actually, making a rocket engine work. Like, this is sort of the super basic, high school version, but getting into the real, no kidding, how do you go build this engine, which is what this book is about, is great. And it really kind of starts there with just understanding some of these basic systems. Okay. All right. So now I'm going to derive the rocket equation. So back to this F equals m dot v exhaust. Now I'm going to be careful and say this is the mass flow rate of the engine. Okay. And that's equal to the mass of the rocket times the acceleration. So F is equal to ma. Now, what I'm going to do here, I'll go ahead and split that into ISP. Okay, and then A, I'm going to bring this over the side. So the change in velocity with respect to time is equal to, now the mass flow rate of the engine is negative the mass flow rate of the rocket, right? The only stuff leaving the rocket is the exhaust. And so that's then divided by mass of the rocket times V exhaust, which I said was ISP G. Okay, I'm going to get rid of the R because it's now kind of redundant and getting a little messy. So dot, remember just time rate of change, I could have written V dot here. And so now when I integrate, we'll have basically delta V, right? The difference between initial and final is equal to ISP times G, and then natural log. And now you can think of this as, I'll write it a couple different ways, kind of initial versus final. So this is the initial mass over the final mass. So you can see here that basically, a rocket keeps pushing. It's not like airplane flying through air where your thrust sets your top speed, right? You have to keep thrusting until your drag is equal. There's no drag in space. So once your rocket's sort of up and out, its top speed, which is sort of this delta V, if you will, because we've kind of ignored gravity and drag. I'll come back to that in a second. It's set by effectively how much propellant you carry. So this is usually not the way we show this formula, because it's really all about how much propellant you carry. So we usually then set ISPG natural log 1 over 1 minus lambda. Okay, lambda is the propellant mass fraction. And so lambda is equal to how much propellant you have versus the total gross takeoff weight of the vehicle. Okay, so this is your very important equation. This is a rocket equation. Now, when you are flying through the atmosphere, and I didn't account here, this should be sum of forces. So really this should have been thrust minus drag minus gravity is equal to that. And so once you come back and account for that, there's about a 5%, sometimes 10% hit that you have to account for gravity. And from that point of view, orbital velocity, like I said, this is 5 miles per second. 8 kilometers a second. Usually, from a rocket point of view, you're going to aim towards a little bit closer towards 9 kilometers per second from a budget point of view. Now, that's also really, really hard to do with just a single stage, and so that's why most rockets are actually, if I'll draw it very basic, okay, most rockets are actually a rocket carrying a rocket, and then there's your second engine. And so what you would do in here, might be your oxygen tank and your fuel tank. You're gonna accelerate with this whole rocket, usually up to maybe 4 kilometers a second, halfway, sometimes a little bit more. And then you're gonna turn off this engine, main engine cutoff, MECO, if you ever heard that on a SpaceX launch. And then you're gonna come through and you're gonna basically disconnect this, blast it apart. And then your second stage is gonna carry on and get all the way to orbit. And then your payload is up here. This is actually the thing that makes you money. It's the satellite you're putting into space, or the astronauts, or whatever. So that's part of this. Is actually each rocket has its own delta V, and they stack. And so there are some solid rocket motors that, while they have lower ISP, they have a lot better density package fraction, and they can get into space, usually using 3 stages. From a liquid rocket point of view, you usually only see it in terms of 1 stage. Okay. And so the last thing we're going to finish with here is just a little bit of this pressure. Okay, so depending if you are, overexpanded or underexpanded, you can get a lot of different things happening with this plume. Basically, what is the air pressure around it? Is it squeezing the plume back down, which would be slowing it, or is it overexpanding the plume, which actually gets the velocity going off, not fully aligned? Both are bad. And so this is called the thrust coefficient. And while I said the force is equal to m dot v exhaust, we also, for this plot, we're going to say it's equal to the pressure of the rocket chamber in here times the area of the throat here. So that already gives you a force. And then we modify it called CF, this thrust coefficient. And so what you see is the area ratio, which is the ratio of A2 to A1, is actually kind of sets your there's this top line here is your optimal curve. If you could have a perfect nozzle that's always expanding so that the velocity is always perfect, it's not being recompressed by the pressure, and it's not being sort of frayed outward by the vacuum. That would be the top line there. And so one choice of engine, so here's an area ratio of 8. It's going to get up to here and then flatten out. Area ratio of 15 up to here and flatten out. A second stage rocket might have an area ratio of 350 because you're really operating in the vacuum of space. And so the area ratio does come back in. That's a little where in this curve, it's sort of, you see it getting better as it gets in altitude. If this kept going up in altitude, you would actually see it start dropping again, okay? And this is a little more detail, and they have this in the book, where you're already kind of flowing that. This is now basically based on area ratio, but the important part here is actually the pressure to the exhaust. P1, this would be P1 inside the engine versus P3, which is sort of the exhaust out here in the atmosphere. And so what this really means is that your performance actually of the engine will go up with higher chamber pressures. And that's why the Raptor engine has some really high chamber pressures. I think if it's 4,000 psi or something like that. You do get better performance, especially in those sea level, of course, but even at your higher, even your vacuum, you can make your bell bigger and get a lot more performance out of it. So those are really kind of the basics, and that's going to be enough for now. We'll come back next time and talk a little bit more in detail on some of this. But basically, the summary, basic 101, go watch that first video I mentioned. Fuel and oxygen are coming to a chamber. You're going from chemical energy to thermal energy into kinetic energy. The exit ratio, the pressures do change it, shown in this graph. And then, I'll come back to that one here in a second. Let me just blank and go here. Rocket equation, it really matters how much mass fraction you can pack in as well as the performance. And then most rockets end up being two-stage to sort of carry for it. Now, the one I just forgot to show you, this is a curve from Transcost with a whole bunch of historical rocket launch systems. And basically, this is the mass fraction. So what ends up happening, really, really small rockets, at some point, the rocket skin is thickness limited, right? Now, it might be a 1/10 of an inch or a 1/4 of an inch would be pretty thick. But anything smaller, and then what's going to happen is someone's walking by with a hammer, hits it, you're going to poke a hole in that rocket. And so your sort of your skin, your structure of your rocket, if you're really, really tiny, has some sort of minimum thickness it can't go under. And so it can get really hard to pack a lot of mass fraction into tiny rockets. Now, the bigger your rocket gets, it's easier to get more mass fraction because now you're no longer thickness limited. You're just your thickness of your tanks are now just set by the pressures. Interesting fun fact: when you do the math, so the strength to weight ratio of stainless steel is about the same as the strength to weight ratio of aluminum. And so when you look at Starship that Spaceship's making, they're making it out of stainless steel. Why? Because it is big enough that the minimum thickness of stainless steel is just fine. They don't actually have to go to aluminum. And so stainless steel is much better from a reusable vehicle point of view. I used to make DOT trailers, and I would never make an aluminum one because they would just, the life cycles, they just crack and go away. But, you make stainless ones or carbon steel, they can go forever. So anyways, from a reusability point of view, you would want to go stainless, but you have to go big enough, which is what SpaceX is doing. So, all right, that's enough for now. Come back next time and we'll dig a little bit further into this book. And this is a great book. So thanks for joining again on this book club. If you like it, like and subscribe. Ask any questions, comments below. This is my wheelhouse, so I'm very happy to really dig into this one. See you next time.